Conversion graphs are a really good way to visually represent how two things compare, how two data values compare. We can use it if we know a conversion rate. If we knew, so in this example, we know that 1 kilometre is 5/8 of a mile, or 8 kilometres is 5 miles. If we know that 8 kilometres is 5 miles, then we know that 80 kilometres is 50 miles. We know 800 kilometres is 500 miles. So there's lots of different values from there that we can gather, and then we can draw a graph and then use that rather than using the conversion to figure out how many miles are so many kilometres, or vice versa. So here we know that, say, 8 kilometres are 5 miles. So that means that 80 kilometres is going to be 50. And we also know then that 100 kilometres is going to be 100 miles is going to be 160 kilometres. So what we can do is we can plot that in the graph. So if we look at the values, so 0 kilometres is 0 miles. So we can put that mark there. 50 miles was 80 kilometres. And then 100 miles is 160 kilometres. And then we can get a ruler and join that up. And there's our conversion graph drawn. So to use the conversion graph to convert 80 miles into kilometres, what we need to do is we go along to 80 miles, and we draw a line up to the graph, and we take it across to the kilometres and see how far that is. So we normally do that with a dashed line. So there's the line, and then we draw across to the y-axis. And because we can see that there are 5 small squares to 0 to 20 and 20 to 40, that means that each small square is worth 4 kilometres. So we can see that 80 miles corresponds to 128 kilometres. Part B, we want to do 72 kilometres into miles. So again, we go to the kilometres side and we go up to 72. Now there's, again, it's 4 units for each small square, so we need to go 3 units above 60 to get to 72. And draw the line down. We can see that it's then in the middle of 40 and 50, so that's going to be 45 miles. We've got an example here of a car hire graph. We're told that Mark's Mediocre Motors charge £30 fixed insurance at the start, and then an additional £15 per day. So you've got, for 1 day it's going to be 30 plus 15, so it's 45. 2 days is 30 plus 2 lots of 15, so they're 60, and then we add £15 each day. So from that we can draw a graph. So we'll go at 0 at 30, then 1 at 45, 2 to 60, 3 to 75, 4 to 95 to 105, and we can extend that line to as many different days as we desire. So how many days then can I hire the car for £200? So we go up to the graph to 200, and we draw our line, our dashed line, to the line, and then extend it down the way. We can see it's just more than 11 days, but that means we can only hire it for 11 full days. What do you notice about the point X? So the point X is the value at the start, and that's the value of the fixed cost. So the £30 that you're being charged for at the beginning is what the X value refers to. Complete the tables, plot the graphs, and answer the questions below. Harry's haphazard car hire is £50 fixed insurance plus £5 per day. So if you have it for 1 day, you've got the 50 plus 5, so that's 55. If you've got it a second day, that's 50 plus 10, so 60. 3 days, 50 plus 15, so 65. And then 70 and 75. For Dave's dodgy car deals, we've got £20 fixed insurance and then £15 per day. So the first day is the 20 plus 15, so that's 35. The second day you have another 15, so there's 50. And then another 15, so 65. Then 80. And then £95 for 5 days. We can plot Harry's graph, our values on the graph. So it starts at 0, was going to be 50. 1 was 55. 2 was 60. 3 was 65. 4 was 70. And 5 was 75. And then we can join the line through that. And then repeat for Dave. So his was 0 and 20. And then 1 and 35. 2 and 50, 3 and 65, 4 and 80, 5 and 95, and then again we can draw the line through all those points. And now we can go and set about answering the questions. So the first one, what do you notice about the slopes? So what we can see is that Dave's slope is steeper, and that's because his daily rate is dearer. Part 2, the points where the slopes touch the y-axis. So those points are the daily insurance cost, the fixed insurance cost. Part B, which firm would you choose if you were hiring a car for 10 days? Well, what we can see is that for 10 days, if we go up on the graph, there's only one line, and it's the black line. It's the one that comes to first. It would be £100. So that'd be Harry. We can't actually see where Dave's would be. It would be a lot greater than that. So then we would pick Harry for that. And what is the significance about where they cross? So they cross at 3 days, which is here. And the significance is that the charges are the same. So the same price at that point. Distance time graphs measure distance against time. The distance is going to be on the y-axis and the time is along the x-axis. And they show basically how far something moves over a given time. So we've got 3 graphs here. We want to try and match them up with the corresponding statement. What we have is, the first statement is a motorbike travels away from home at a steady speed. And that's going to be the third graph. And that's because it's a steady speed. The distance over time is constant. It's a straight line. It's sloping up the way. So the distance is moving away at a steady rate. The second statement then, a car remains parked in a car park. So that means the distance isn't changing. So the distance remaining the same. So what we have is that's going to be the first graph. So the distance is a horizontal line, implying that it's not moving anywhere. And then the third statement, a runner runs a steady pace. So we're going to expect a straight slopey line for that. To the end of the track, turns round and then runs at the same speed back again. So we can see that's going to be the middle graph. And that's because it's a slopey line up and then a slopey line down. So the distance away from you is increasing up until a point, and then it returns. The extension, draw a time graph to show a man going out to take his dog for a walk. So he's going to walk steadily for some time. His distance from home is going to increase, and then he's going to stop at a shop. He then will take a while to buy his newspaper. So his distance is not going to change. And then he will return home again. So the line should return home. Obviously, if the dog has to stop for any business, there will be a further horizontal line. But since we're not told any of those details, we assume the dog was well behaved. This next distance time graph is about describing what happens at each point. So at point A, the journey starts and the distance is decreasing, so it looks as if they return home. And the line is a steady slope, so therefore it's at a steady speed. Part B, the distance is stopped. The distance isn't changing, so therefore they've stopped for some reason. C is another stopped point because the line is horizontal. Between there, there's been an increase in distance, so they've returned. What you might have is the person has left work and is going home. They've stopped to answer a phone call possibly and forgotten something at work, so they've returned back to work, at which place they've returned to get their belongings. Then their journey started again and they've returned home. They've had to stop and make a U-turn, so their diversion has gone away again. Maybe the road's been closed or something. So at this point D, they're changing direction. And then the last part, the journey has ended and they are back home again. In this last example, we're expected to draw a distance time graph. So James decides that he's going to get fit and goes for a jog. He begins running at 6 meters per second. Now, a speed of 6 meters per second does exactly what it says. So James will travel 6 meters every second. So that's what a speed of 6 meters per second implies. But after 15 seconds, he decides to slow down. So that means he travelled at 6 meters every second for 15 seconds, meaning that he's travelled 90 meters. He slows down and jogs for a bit at 4 meters per second. Again, that's 4 meters every second. And he does that for 30 seconds. So that's going to be 120 meters. So if it's 4 meters every second and it's 30 seconds, we're doing 4 multiplied by 30 to get 120. Struggling for breath, he went slowly in at 2 meters per second again. That means he travels 2 meters every second. And that's for the last 5 seconds. So that's 10 meters. And what we're doing there is 2 times 5. Now you might be familiar with speed equals distance over time, and drawn a triangle from that if you want to work out speed, you can cover up the speed and you get distance divided by time. If you wanted to work out time, you would divide distance by speed, and if you wanted to work out the distance, you'd multiply speed by time. So that's what we've done without physically actually showing that, but we've multiplied the speed, so 6 by the time, 15 to get what our values are. We've just kind of used it by logic. So I've got my set of axes. I've got time along the horizontal and distance along the vertical. The total time was 50 seconds and the total distance was 210 meters. So the first stage of the journey was running for 15 seconds to get up to 90 meters. So that's going to be to here. He then ran a further 120 meters in 30 seconds, so that's going to take us up to 45, and another 120 meters will take us up to 210. The last 5 seconds was a further 10 meters, so that would be there. Joining up all the points, we get James's distance time graph to look like that.